Yes, hello there. My name is Ashraf, and I'm here to take us through forces in beams and frameworks. This is going to be our first topic, and I wish you the best of luck as we go through this. Now, before we get into the topic, we need to familiarize ourselves with certain terms that will come in handy as we go around the topic. So, the first of these is coplanar, and as you can see, coplanar comes from two words, that is co and planar, which means same plane. Co, same, then planar is from plane, which means same plane. So coplanar means same plane. And you know you have three planes, the X, the Y, and then the Z. So if we say coplanar, that means whatever we are handling is from a single plane. It does not cross into the other plane. Then next, we are going to have concurrent. And concurrent is also from two words, co and current. What this means is that the forces that we are handling are from a common point. They are concurrent forces. They are from a common point. So this can be 7 newtons, this can be 8, this can be 4 newtons. So all these forces are called concurrent because they are from the same point. So then another one is non-concurrent. So non-concurrent, as you can tell, the forces are from different points. So this can be 4 newtons, this can be 16 newtons, this can be 7 newtons. These are all forces but from different points. So they are non-concurrent. So we can combine these two words to form a system of forces. And as you can see, these can be called concurrent, coplanar forces. Why? Concurrent because they are coming from a single point, and coplanar because they are in the same plane. All the forces that we are going to handle in this course are coplanar, so don't worry about that much. And then this other next one will of course be non-concurrent. Why non-concurrent? Because they are originating from different points. Non-concurrent coplanar forces, the second one. Then finally, the last term that we can look at here is coplanar parallel force system. And this is going to be in a beam. So if you have a beam, this is our beam. We may have forces acting on this beam like this, and then we can have reactions that support this beam. As you can see, all the forces on this are parallel, which makes it a parallel force system. But all these forces are in the same plane, so coplanar. Okay, now our next activity is going to be dealing with concurrent forces. So now let us look at concurrent forces. Let's explore an example. So perfect. The example that we are exploring today is this, and we have a diagram here with forces, and the question is saying determine graphically. Why graphically? Because we can actually determine this using numerical methods. So determine graphically the magnitude and direction of the resultant force. Okay, now to do this, we need first of all a scale. Why do we need a scale? Because there is no way you can represent newtons on a paper. So we need to convert these newtons into a unit that you can draw on paper. So my scale here is going to be 1 newton is actually equal to 5 millimeters. So this is the scale I'm going to use. And that would imply that 4 newtons would become 4 times 5, which is 20 millimeters. Then 6 newtons would become 30 millimeters. Then 3 newtons would become 15 millimeters. And finally, 2 newtons would become 10 millimeters. Now that we have the scale, we can proceed and draw what we call the Bose notation. The Bose notation is an accurate representation of this system here. So I'm going to pick my set square very fast here and draw this. So start off with a horizontal line. Then on this horizontal line, I'm going to put a vertical line. And this vertical line represents my 2 newtons. Then I'm going to put a horizontal line for the 6 newtons. Then I put 45, so I'm going to use my 45 set square. We are drawing what we call the Bose notation. So 45 there. So this is 4 newtons. And finally 60. So let us put 60 there. So 60. And this is 3 newtons. Okay, so we need to name what we've just drawn. And what we've just drawn is what we call a Bose notation. So I'm going to call this the Bose notation. Then to make the Bose notation complete, we need to name this figure. So I'm going to name these forces. Follow me here. So this first force, 2 newtons, I'm going to call it AB. So this first force here is AB. Then this next force is going to be BC, this one. Then this is going to be CD. Then this is DE. You realize that the first space where you started from will have 2 letters like this. So the first force is AB, BC, CD, DE. Perfect. Now after drawing the Bose notation, we draw what we call a force diagram. And to draw a force diagram, simply follow me here. You're going to slide the line AB, start from where you started from. So I'm sliding line AB and I'm putting it somewhere here, like that. Then AB is 2 newtons. And from our scale, realize that 2 newtons is actually 10 millimeters. So measure 10 millimeters. So this is AB and it is going down. So I outline this portion. It is our AB. Then get BC, proceed to BC. So get that line of action of BC. Bring it to point B. Draw a line. Then BC is 6 newtons. 6 newtons is actually 30 millimeters. So I'm going to measure 30. So this point here is C. Then I outline this. Then I put my arrow like that. Then we get CD. So CD. Then CD is 4 newtons. 4 newtons became 20. So I measure my 20. So this is D. So this is CD, 20. And finally we have DE. DE, so slide line of action of DE and also put it there. So put it here like that. So 3 became 15. So I measure 15. And this here is what we call a force polygon. So to make it complete, I join the first point to the last point E with a dotted line like that. Now follow me here. The forces are going in one direction. This is this. So the resultant will have to go in the opposite. If this person is moving from A to B to C to D to E, another one can move from A direct to E. So this would be our direction for the resultant. Now remember, they want us to get the magnitude of the resultant. So the magnitude you simply measure. As I said, guys, this here is the resultant. So if they're asking for this direction, we've already shown the direction. Then the magnitude, simply measure this distance. As you can see, we are getting a 4. So magnitude of the resultant is actually equal to 40 millimeters. Yes, we measured 40 millimeters, but the resultant is a force, so it can't be measured in millimeters. So we need to convert that back to kilonewtons. And according to our scale, 5 millimeters is equal to what? Is equal to 1 newton. So what about 1 millimeter? This will be 1 over 5 newtons. So 40 millimeters would be equal to 40 times 1 over 5 newton, and you get 8 newtons. So the resultant here becomes 8 newtons. So that is the resultant. Then I need to introduce you to another term, and this is what we call the equilibrant. Now the equilibrant has the same magnitude as the resultant. So the equilibrant is also 8 newtons. The only difference between a resultant and the equilibrant is the direction. So if they asked for the equilibrant here, the equilibrant goes in the opposite direction to that of the resultant. So if they wanted the equilibrant, we would have put an opposite direction to that of the resultant. Let me hope it makes sense. We are going to keep seeing this in the coming examples. So no worries. Perfect. Okay, so in our next example, you can see that we have a non-concurrent coplanar force system. The forces this time are non-concurrent. They are originating from different points. So how can we handle a number like this one? Still, we start off with a scale. So we are going to say that our scale here, I'm going to say 1 newton is actually equal to 7 millimeters. That would mean that my 4 newtons would become 28 millimeters. Then the 3 newtons would become 21 millimeters. And then the 5 newtons would become 35 millimeters. Perfect. Now after drawing that, we go ahead and draw our Bose notation. Remember, our Bose notation is an accurate representation of this. So I'm going to draw 3 lines. So I'm going to start off with this one here. My next one is going to be a little distance down, any distance that you want, and finally somewhere here. Then on the first line, I'm going to draw an angle of 50. For purposes of this video, I'm simply going to measure because angle construction is out of the scope of this video, but I'm sure you know how to construct angles. So this is 4 newtons. Then somewhere here, I'm going to mark off 60. So this is 3 newtons. And then somewhere here, I'm going to mark off 20. So this is 5 newtons. And just like that, we've drawn our, we call this a Bose notation. So let's label it as that. So Bose notation. And to make the Bose notation complete, we need to label the forces. So I'm going to start off by labeling my forces. You can start from anywhere. Personally, I'm going to start by labeling this force down here. So I'm going to say this is A, B. So this force 5 newtons is AB. Then this one will be B, C. Then this will be C, D. Just like that. And as we said in the previous example, you realize that the first space here will have 2 letters. In this case, A and D. In the previous example, if you remember correctly, we had A and E. Perfect, in that first space. Now, after drawing this, we now need to draw the force polygon. So to draw the force polygon, we start off with the first force. So I slide this line to any point that I want. So I'm putting it here. Then AB is 5 newtons, and we saw that 5 became 35. So mark off 35 on this line that you've drawn. So this is A, B. This is the direction. Then we proceed to B, C. So slide this force BC, put it right here. So 4 newtons became 28. So this is C. BC, and finally CD. So slide CD. Then CD is 3 newtons. 3 newtons became 21. So mark off 21 here. So this is D. And just like we did last time, you join the last point to the first point with a dotted line. And just like that, we've drawn our force polygon. So let's name it right away. Force polygon. So that is our force polygon, and as you can see, the direction that was taken here is A to B to C to D. So another person can decide to go from A straight to D. So that would show that this is our resultant. The direction of the resultant is given, so you need to get the magnitude. So the magnitude, you simply measure this length, and as you can see, I'm having 49. Yes, so the magnitude is equal to 49 millimeters, but resultant is a force, it can't be measured in millimeters, so convert this back to newtons, and according to our scale, we shall have 49 divided by 7, and we get 7 newtons. So the resultant here is 7 newtons. Now, another question may come and they ask us to draw the position of the resultant relative to this diagram here. In the previous example, where we had the forces concurrent, if they told us to draw the resultant relative to this system of forces, we would simply slide this resultant. We would simply slide and put it at this point. Why? Because all the forces are originating from the same point. So that would mean the resultant is also originating from that same point. But it's not the case in this case here where the forces are non-concurrent. The forces are coming from different points. So if I'm to slide this resultant, where am I going to put it? So to handle this, simply choose a point inside the force polygon, then join. So I'm going to name this point O. So join all these other points to O, like that. So after joining, we get C0, B0, A0, and D0. So you're going to slide all these lines into the spaces up there. Now, I'm going to start off with A0. And I slide line A0 in the space of A here. This is what I'm talking about. Slide line A0 into the space of A somewhere here. Like that. Don't mind about where it's going. We are going to see how to handle. Then I'll slide B0. This is B0. I'll slide B0 and put it in the space of B. The space of B is this. But I'll start from where A0 stopped. So, there, you can see that I started from where A0 stopped. Then there, in the space of B. Then I get C0. So get C0 and put C0 in the space of C, which is this. Then finally get D0 and put D0 in the space of D. So we are sliding D0. We are putting D0 in the space of D. So once I do that, realize that A0 and D0 are meeting somewhere. And this point where they meet, that's where the line of action of the resultant passes. So I simply slide this resultant and put it at that point. So I can be certain that the resultant, the position of the resultant relative to the forces here is that position. Remember we said the resultant is equal to the equilibrant in magnitude. They only change the direction. So if this is our resultant, if the question wanted the equilibrant, we would draw the same line at the same point but simply reverse the direction. And that, ladies and gentlemen, is how we handle concurrent and non-concurrent forces. In our next video, we are going to look at forces on beams, an example like this one, and we see how to determine those reactions. So see you in the next video. Bye for now. I remain Ashraf.